This audio abstract was created and produced by Arcadis. All statements, opinions, interpretations, and conclusions expressed belong to the individual speakers and do not represent views or policies of the Groundwater Monitoring and Remediation Journal, Wiley Publishing, Arcadis, or any other entities. The rapid increase in the interest in PFAS contaminants is one of the most dramatic and important trends in groundwater remediation research and practice. This interest is driven by several factors, including the anticipated low regulatory levels, complex transport properties, and unique release scenarios for these compounds. As a result, we anticipate there will be many sites where contaminant assessment and management of PFAS at the Groundwater-Surface Water Interface, or GSI, will be necessary. Therefore, in this column, we highlight some examples where PFAS transport between groundwater and surface water is important, and summarize current practices and developing technologies for characterizing and managing PFAS at GSIs. I've asked Dr. Amar Wadhawan, who is a co-author of this article, to help summarize some of the key features and points. Amar, would you mind introducing yourself, a little bit about your background, your area of expertise, your role of Arcadis?
Sure. I'm Amar Wadhawan. I am a principal engineer at Arcadis with over 17 years of experience in contaminant fate and transport and site investigation and remediation. My background is in environmental engineering and science with a master's at Stanford and a PhD from Hopkins. At Arcadis, I lead sediment and groundwater investigation and remediation projects, focusing on a varied list of contaminant classes, including chlorinated solvents, PAHs, PCBs, and then our favorite, PFAS. Also, as part of the Arcadis' technical communities of practice, I lead the PFAS in aquatic systems focus area, and as well as the phytoremediation practice area. So these would include installing piezometers and stilling wells, calculating, establishing, the difference in levels of surface water and groundwater, establishing gradients, and then using those measurements to really calculate fluid flux. And then with concentration, one can arrive at the mass flux. And then there are other tools as well. Seepage meters are common tools that are available to assess seepage velocities across the groundwater surface water interface. But then there are upcoming technologies as well. So there are technologies that are focused on really addressing the groundwater surface water interaction in streams, and to that end, there are the stream bed point velocity probes that not only measure the fluid flux, but then by measuring concentration in pore water, one can get an assessment of the mass flux. And then similarly, there's the passive flux meters in streambed passive flux meters that are available. And then more innovative tools like the T-flux, which we have talked about in the publication, which has an array of sensors looking at pressure, temperature, at that interface to ultimately arrive at the same Darcy flux across the groundwater surface water interface. But more importantly, it can allow for a time series of measurement to really address transient conditions.
Yeah, I think what's really driving this need for improved characterization and basically a higher level of detail and resolution, as you mentioned, both space and time, is we need conceptual models that capture that information more so maybe than we typically would do for other contaminants, because of certainly the complexity and scale of this problem. And those conceptual site models, of course, ultimately drive our understanding of risk posed by these contaminants, and then can allow more appropriate remedy designs or tailored remedy designs or surgical remedy designs. As you were talking, one other, I think, need that is unique to PFAS is to better understand the phase in which PFAS is transported in surface water settings. In particular, PFAS is known to absorb to sediments. It accumulates at the air-water interface. It can partition into an oil phase if present. And particularly in dynamic flow settings, like in stormwater events, you may have not just variable flow, but variable concentrations of PFAS, and that concentration distribution, that mass distribution of PFAS, may be associated with different phases at different parts of the flow event. So just generally, I think we need a better understanding of PFAS transport in storm events and high flow events, transient events, and then tools alongside that to characterize that transport. So let's move into mitigation and management approaches. Amar, what are some of the options that we have that we can draw from existing technologies, and what are some of the promising developing technologies specific to PFAS?
So when it comes to PFAS, as we all know, they are persistent. They are very hard to biodegrade, or they don't biodegrade that readily. And they may transform from long chain precursor to short chains, but then those short chains persist in the environment. So really, most of the work that has been done is addressing the PFAS removal through sorption or ion exchange when it comes to groundwater treatment, and controlling the source. So for any remedy, right, if there is an ongoing source, the remedy is basically in place for perpetuity. So the source control comes at the forefront for any groundwater, surface water remediation or remedial strategy. So source control meaning removal of the contaminant, removal of PFAS, whether it's in soil by excavation, if there's concrete leaching, sealing the concrete that's contributing to PFAS in runoff into the surface water. And then in streams and ditches, right, when groundwater is discharging to surface water, or even surface water is recharging to groundwater, or there are these sorbent flow-through barriers that have been developed and being tested for PFAS. And in this case, the PFAS-tailored sorbent is sandwiched or embedded into a geotextile mat or fabric, which is then emplaced over the groundwater discharge interface. So it's emplaced either in a stream or a stormwater infrastructure. And the premise is the same as a PRB or a permeable reactive barrier, that when the groundwater is discharging through this reactive mat, PFAS are removed on the sorbent that's embedded in the mats. So there are some of the technologies that are being developed. I should note that most of them have yet to be widely demonstrated for PFAS control and removal, but they are being slowly commercialized. So,
Amar, you mentioned treating concrete to seal it, and that falls in the broad class of BMPs, best management practices, at least as I think about it. And I think that's a pretty important feature or component to PFAS treatment and management for surface water settings.
So PFAS-specific treatments for stormwater conveyance, definitely a big consideration, because stormwater plays a huge role in impacting surface water at many sites that have PFAS impacts. And as you mentioned, sealing up any concrete stormwater infrastructures, but then in some cases, really using some tailored materials or tailored technology that are coming to the market that are specific to PFAS. So one example that I gave was using these PFAS specific sorbent mats, and I could see that these mats could be used to line stormwater infrastructure or conveyance systems, where to lessen the load, to lessen the discharge, or even in some cases completely eliminate that discharge from stormwater to surface water. And we haven't really touched on the PFAS foam, right. PFAS association with foam yet, and that's an area of active transport for PFAS, where that wouldn't be the case for PCBs or even solvents. But as we know, PFAS associate at the at the air-water interfaces, and PFAS in foam can present a really high loading in a small mass of discharge from surface water to groundwater to even soils. So,
yeah, in fact, in the article we highlight a small vignette that describes a real-world example where foam that is generated on the surface of a lake due to wind action is blown onto the lake shore surrounding the lake, and then subsequent infiltration into groundwater transports high loads of PFAS into the shallow groundwater around the edge of the well. And PFAS in that foam has been measured at very, very high levels. And certainly we can think of lots of examples where foam may be transient, but may be meaningfully present in certain flow conditions. And having systems that can target that foam, in some ways that could be used to our benefit. That's a waste concentration process. And proportionally high mass of PFAS can be removed if we can target that foam and address it.
So with PFAS, there are a lot of challenges, but then with challenges come opportunities for us to, use our creative minds and develop innovative solutions. So I think the biggest challenge on an investigation side of groundwater surface water interaction is continued development of these innovative tools that can really get to the better understanding of PFAS fate and transport and fluid and mass flux under more dynamic systems and provide that high resolution spatial and temporal data along with real-time sensing. So considering that or building that into existing model to better predict PFAS fate and transport from groundwater, from soil to groundwater to sediments to pore water and surface water, I think is really needed to better understand and develop holistic site conceptual models. On the treatment and management side, as I was saying earlier, that there are these new technologies that are being developed, the tailored sorbents, some of the destructive technologies that have shown promise at a limited lab scale, and so there is need to scale up those technologies to have a better understanding of their performance and limitations at a field scale and increase their deployments. So lots to be done, but it's an exciting time as more and more innovative technologies, innovative models, innovative tools are being developed and progressing the field here. So.
Well, that's great. Thank you, Amar. Appreciate your conversation today and your contribution to the article.
Yeah, thank you, Craig. Great discussion.